Alright, here is my video guide for lesson 10.1.1, first lesson in chapter 10. And this whole first part of chapter 10, all the 10.1s are really going to focus on giving us a deeper dive into circles, different circle vocabulary, more special qualities of circles. And with that, today we're going to get some new vocabulary, and we're going to dive into the perpendicular bisectors of a chord. This lesson here, I've cut some things out because in some of these problems we needed a resource page and we needed to work hands-on, and we can't do that online. And so you'll see I am going to skip 10-1, I'm going to skip 10-4, and so really all I'm doing today is 10.2, 10.3, and 10.5. And that's all I have for that, so let's get into the first one here, 10-2. All right. A line segment that connects the endpoints of an arc is called a chord. Thus, AB in the diagram is an example of a chord. And so that's a new vocab word for us, chord. And here's a picture of a chord. A to B, that line segment that comes across the circle there, that's your chord. What makes that different than a diameter is a diameter would have to be cutting the circle perfectly in half, something like this line down here. When it doesn't cut the circle perfectly in half, but it does go through the circle like we see here, we call it a chord. And that's the first vocabulary that I want us to all know, that word chord. All right. The next part, one of the ways to find the center of a circle when given an arc is to fold it so that the 2 points of the arc coincide or lie on top of each other. And if we did 10-1, that's what they would have had us explore, is they would actually gave us an arc that we could have folded, and we could actually find that center of the circle based on it. Because what happens is if you folded B onto A or vice versa, you create this crease here. And that crease really is cutting your circle perfectly in half, because really what you did was fold your circle or your arc perfectly in half. And so we'll go on here to the actual question, and it says if you fold AB so that A lies on B, what is the relationship between the resulting crease of that chord? Or sorry, the resulting crease and that chord? Well, like I said, because we folded that arc in half, we're actually cutting the circle perfectly in half, and we're cutting that chord perfectly in half. So actually that chord is now getting bisected by that crease, and what else is happening is that it's forming a perfect perpendicular line to it. And so we have a 90-degree angle there. And so the best name for that crease and the relationship between that crease and that chord is that for A, the crease is a perpendicular bisector of chord AB. Again, we know that's a perpendicular bisector because by folding that chord by folding that arc in half, we are actually creating equal parts on the left and on the right, and that makes that bisector portion of it. And that crease does form a perfect 90-degree angle here, so we know that it's perpendicular. All right. In B, it says the tree fragment in problem 10-1 was an arc between points A, B. An arc is that darker part, so A around to B on this dark line, that would be your minor arc here. However, the missing part of the tree formed another larger arc of the tree. With your team, find the larger arc formed by the circle and points A, B above, and then propose a new way to name that larger arc. All they want us to see here on this is that AB is shorter than if you went around the other way, that if you went around this way. And so they call this right here, A to B, that dark line, they call that the minor arc, and they would call this red part here the major arc. And that's terrible as I got over there, but they call that part from A to B going around the long way, they call that a major arc because, well, one, it's longer than the other one. And I guess that's really my main point, is that they make the majority of that circle, that red majority is the major arc, the smaller part is the minor arc. And then propose a new way to distinguish it. We're actually going to go into problem C for that right away. So in problem 10-1, the tree fragment formed the shorter arc between two endpoints. The shorter arc between the endpoints is called the minor arc. I said that, and it's written AB with that little roof over the top of it, signifying that it's just A to B in that minor arc. and then the larger arc is called a major arc, the red one, and is usually written with 3 points. And so they write it as ACB because of point A, C, and B. And then they just say ACB with that bigger roof over it. And so major arcs generally written with 3 letters, minor arcs generally written with 2 letters there. And then what do you know about AB? If the minor and major arcs are the same length, that would mean, for part C here, if your minor arc and your major arc, and I'm going to get rid of this here, the idea here is if your minor arc was the same as your major arc, that means your circle must be cut perfectly in half. And so that your minor arc here, and it's not going to be perfect, would be the same as your major arc down here. It would probably be like the case where you couldn't even call them minor or major because they're the exact same. But what that would mean is that that chord or that AB that would be cutting it, that would have to be a diameter. So if your minor and major arc are the same, that means your chord is a diameter. All right, so there's the answers for this first problem, A and C, the ones we really have to write. The answer to B is really in here in C, and so make sure you pay good attention to what C has to say. That's that idea of minor arc, major arc, and how we write those. Minor arc being 2 letters with the roof, and major arc being 3 letters with the roof. And we'll move on to 10-3. Okay, we are actually here in this problem going to prove that crease, if we folded it, you know, A on top of B, that crease really is a perpendicular bisector, but it's a pretty interesting way to go about it. And so folding this results in a point that seems to be at the center of the circle, but how could we prove that that line is actually bisecting that chord and will pass through the center? And they do this to consider this. First, assume that the perpendicular bisector does not pass through the center. And this is going to be a proof by contradiction. So there's different ways we can prove things. This proof by contradiction is pretty much saying like, well, we think, and our assumption is that when we fold this, it should cut through the center. So let's say that it doesn't cut through the center. And then if we can't, if it doesn't make sense here, then really we have a proof by contradiction. And so we'll start that here, and it says, according to our assumption, if the perpendicular bisector does not pass through the center, and I should change this to just calling it C because that's what they call it. So our first part of our proof of contradiction is to say that this point here is the center, but that point C, that center point, is not on our crease line. All right, and they want us to copy it onto the diagram. The diagram's already right here. All right, and now we need to say, are these triangles ACD and BCD congruent? And so I'm going to actually draw these lines in here. A to C. I'm actually going to use a different line. One of these lines will probably be better because it's straighter. A to C and C to D. So we got that triangle. And then we have B to C and then C to D. And so those are my 2 triangles. Now it wants us to say if these 2 triangles are congruent. Now when I'm looking at this here, these triangles, to me, of course, they don't look congruent at all right now, but we actually have to take into account, you know, what this is saying. What we do know is that AD and BD are congruent. So AD is congruent to BD, and that's just given. Those 2 tick marks are telling me that those are congruent, and so that must be given. I actually do know as well that AC is congruent to BC. Now this one is the confusing one because it looks like AC is shorter than BC, but the idea is that's the center point, right? This point here, I'll try to make it in red. That's the center point. And if that's the center point and that's the assumption that we're working with, that must mean that CA or AC is a radius and that BC is a radius, and that if this is a circle, those radiuses must be the same. And so I can actually say that AC and BC must be the same, working under the assumption that we are. All right, and then the last one here, I can say that CD is congruent to CD because that's actually a shared line right there. So this is just taking the tools of triangles that we already know, and it's just a harder proof because we have to work with the assumptions that they gave us, not really as much with our eyes. We have to work with that idea that that's a center point there. All right, but with this, all these statements said, AD congruent to BD, AC congruent to BC, and CD congruent to CD, I have just proved that these two triangles are congruent. So the triangle ACD is congruent to triangle BCD, and that's congruent because they actually have side, side, side congruency. All right, now here's the part where they really want us to focus on. And so explain why this result from part B actually contradicts the original assumption, that is that the center must lie on the perpendicular bisector, or explain why the center must lie on the perpendicular bisector. And really the idea here is because that distance AC and BC, if it didn't lie perfectly on the center, it wouldn't be a radius. And that's how I'm going to write that there. We wouldn't have the triangle congruency. We wouldn't have triangle congruency if the center, or if the center, if that center, or sorry, I'm going to say it like this: if the perpendicular bisector did not cut through the center. And so I know that that's kind of a weird way to write that, but to me it makes sense with the idea that this perpendicular bisector, that crease, has to cut through the center. Otherwise we wouldn't get this congruency here. And that's what this was just trying to show us, that under our assumption with that being the center, we are allowed to do that. But in actuality, we would need that perpendicular bisector to go through it. All right, we'll move on to the last one. I think I'm going to do that in the second video.